I now want to talk about center of mass. Center of mass is something that is actually not a part of the curriculum for this class. I don't really know why, because we do actually need to talk about the center of mass. That's where all the free body diagrams emanate from. But because it's not a part of the curriculum of this class, I actually, where'd my roll of tape go?
Kicked it left at 3.0 meters.
Thank you. I kicked it to the left 3.4 meters. Thanks. I found it. Evidently, I picked it up at some point, or somebody else did. Okay. So what we're going to talk about is a bunch of stuff that is interesting and useful, but not necessarily a part of this class. I'm going to put at least one equation on the board. We're going to talk about how it works, but again, this is not stuff that you're responsible for the curriculum for this class. So we need to define center of mass. There are a couple of different definitions of center of mass. One of those is if you take an object and you throw it in the air, it will rotate around its center of mass. So you can see the center of mass of this object is located right in the middle. If I take the foam pill that I have, it will rotate around its center of mass as well. You can see where the center of mass of this object is. I can even do it with Captain Underpants. He will rotate around his center of mass, and the roll of tape will rotate around its center of mass as well. Another definition of center of mass is if you push on the object at its center of mass, it will cause only translational motion and not rotational motion. I'll translate that for you. If you push on the object at the center of mass, it will only move linearly. You will not rotate the object. That is true with this one. If I push on the center of mass, it will actually only cause it to move linearly. It will not rotate it. But there's an issue with that, because sometimes if you take and you push on the center of mass of the object, it doesn't work. So does the center of mass of the object have to be physically located on the object? No, it's not a physical location on the object. It is where all of the mass can be considered to be concentrated for the purposes of translational motion. It is where we can consider all the mass to be for the force of gravity. The force of gravity acts on that particular mass if we talk about the whole object at once. Another piece having to do with center of mass. Sam, come on up. Come up here for me. Okay. Please do me a favor, bend over, touch your toes. All the way down, touch your toes. Very nice. Can you golf club? Ooh, look at you. Oh yeah, that's right. That's awesome. Good. Good. Come on up. All right. So what you can clearly see, he can bend down and touch his toes. Good. Now what we're going to have you do? Come over here. Please put your heels against the door. Heels all the way against the door. Good. And now bend over and touch your toes. Oh, good. Thank you very much. Good. Thank you for illustrating. That's great. That's perfect. Come on. Now, what you saw here is he had no problem touching his toes here, but when we put him against the door, he cannot touch his toes, right? You fell over. Agreed. Okay, no, turn, looking for you to turn. Good. Okay, now, bend over, touch your toes. Good. Come on, back up. And it's important to understand and watch what he does when he bends over to touch his toes that he cannot do with his back against the door. Again, and back up. One more time, this is fun. Down and up. Who can tell me what it is that he is doing that makes it so that he can touch his toes now, Chattis, but he couldn't before when he was against the wall?
He shifts on his weight back so that he
Great. Thank you. We'll walk through this. The technical term I want to talk about is the fanny. Notice what happens with the fanny. You bend over. Watch the fanny. When we bend over, the fanny goes backward. Right? You can see it. It's the fanny. It's a technical term. Yeah, that's fine. I can handle it. Okay. So when I bend over to touch my toes, my fanny goes backward. The reason for that is to compensate for the fact that the rest of my body goes in front of my toes. What it does is it keeps my center of mass over my toes. And we're going to talk about what happens if you cannot keep the center of mass over your toes. You do know my exceptional drawing capabilities, so please observe as I draw your body. This is your feet, these are your legs, this is your body, this is your head, and these are your arms. As I said, the center of mass is where I worked hard on this. Is where the force of gravity is exerted on your body. Now, what happens is, if that center of mass gets in front of your feet, you get what is called an axis of rotation at your toes. and your body rotates around those toes. Sam, you felt that, correct? Right? So what happened here is he was unable to push his fanny backward, which made the center of mass go in front of his toes, and therefore caused him to rotate forward. What happens here is it actually applies a torque to his body. Now, torque is another thing that is not a part of the curriculum for this class, but torque is FD sine theta. So tau is the Greek letter, and it stands for torque. And this is clearly the force that we're talking about. This right here is called the lever arm, and it's the distance from the axis of rotation. So the larger the distance from the axis of rotation, the larger the torque, and hence the larger the tendency for the object to fall over. This is related, don't worry. Have you ever had an opportunity to watch a child learn to walk? It's totally unfair. Because a child has what size head relative to their body? It's very large. Relative to when they get older, the head is very large when you're small. What does this do to the center of mass of a child? It raises the center of mass relative to the size of their body, right? So their center of mass is actually higher, which means it's completely unfair because there's a larger amount of torque and it's harder for them to learn how to walk because they fall over more easily. It's not fair at all. There's also a relationship between I'll try this again. There's also a general comparison between where the center of mass for a man and a woman is. Does anybody know the difference in general for the center of mass of a man versus a woman? Sam?
It's for women, it's a lot lower.
For women, in general, it's not always true, but in general, for a woman, the center of mass is lower than for a man. This is why women are considered to be more graceful, right? Because if their center of mass gets in front of their toes, for example, there's actually a slightly smaller torque acting on their body, so they have less tendency to tip over. So women are more graceful. But please pay attention. If you flip a man upside down, he is actually more graceful upside down. Because if you flip him upside down, his center of mass is lower than for a woman, and therefore it's easier for a man to balance upside down. So that's why men are more graceful upside down. All right. Don't worry, we're still talking about center of mass. I'm going to compare it, we're going to talk about something slightly different in just a moment here. Today's desktop picture is Geneve. If you recall, we had a bunch of kids on the tennis court a little while ago. Now we have just one. And you can take any moment and make it look really good. Like, look at this. She's like posed and ready to hit that tennis ball. It's like a great moment. What you don't know is that she then swings and misses the ball. But look at that. I mean, that's perfect. And then she misses it. But that's okay. Okay. So what I'm going to show you is a video of something called the Fosbury flop. Anybody ever heard of the Fosbury flop? Okay. What's the Fosbury flop?
It's like how people high jump now.
It's how people high jump now. But notice, in 1968, Dick Fosbury won the Olympics by doing what is called the Fosbury flop, because he invented the Fosbury flop. So what we're going to look at first is people doing the high jump before 1968, before Dick Fosbury invented the Fosbury flop. So please watch here. This is pre-1968, so this gives you an idea of how people used to try to do the high jump.
Until 1968, everybody tackled a high jump using the same technique. And then in Mexico in '68, along comes Dick Fosbury and shows the world what at the time was considered to be a radical and revolutionary way of high jumping, which nobody had even considered before. was to disrupt the one convention of high jumping, which was the only way to go over that bar was on your front.
So again, I'm going to show you what Dick Fosbury did, which was he changed the total approach to jumping over the bar. Before Dick Fosbury, everybody went over the bar forward. And this is just a bunch showing you Dick Fosbury doing his own jump here. But the idea is, instead of going forward over the bar, you go backwards over the bar, bending your body like this. And what happens when you do so is it adjusts where you can keep your center of mass. And remember, for projectile motion, the only thing that matters is the center of mass. So if you do the Fosbury flop correctly, and this is Dick Fosbury doing the Fosbury flop, when you go over the bar backwards, you bend your body like this, and your center of mass ends up being down here. And if you do the Fosbury flop correctly, your center of mass actually never clears the bar. Your body goes over the bar, but your center of mass doesn't. But again, as far as projectile motion is concerned, it's only the center of mass that really matters. So I'm going to draw a direct connection right here. Dick Fosbury won the 1968 Olympics because he created the Fosbury flop. He didn't win in 1972 because other people had learned from him and started doing the Fosbury flop and beat him using his own Fosbury flop. So Dick Fosbury was not the best athlete. However, Dick Fosbury did his physics homework, and therefore he won the Olympics. So I'm drawing a direct connection here. Here's the message of the day. Do your physics homework, win the Olympics. You think I'm kidding? I just showed you proof. Do your physics homework, win the Olympics. Ladies and gentlemen, people, thank you very much. I hope you enjoyed learning with me today. I enjoyed learning with you.